Alright, welcome to another AQA A-level chemistry video. Today I'm going to make a video on pH curves and titration part 2. The part 1 will be left in the link in the description. In the last video I talked about titration and titration technique, indicators, why we do titrations. And remember that we do titrations to give us information to help us with our calculation overall. So we do this to find a tighter volume, and if we already know the moles from a known concentration, we have then the moles, and then we'll do a titration to work out a tighter volume to help us work out our unknown concentration. We also looked at other things in terms of other things we need to look at in a titration in terms of accuracy, concordant results. So remember that concordant results are values that are within 0.1 centimeters cubed of each other. That's the only ones that we really really include. Other than that, we don't really use those types of results. We looked at what the diagram looks for a titration reaction, the equipment that we will be using, and just a brief overlay on how to do concentration calculations with moles and volume. So kind of a brief overview on that. So this video is me going to be talking about the different types of graphs. I also talked about the why there's those specific trends in graphs. So why the graph behaves in a certain way, why pH and volume of base added graph looks like this, and what each part represents, so the equivalence point, so on and so on. So sorry about that. All right, so I'm not gonna talk too much. I'm just gonna go straight into this video, and yeah, that's it. So the first I'm gonna show you 3 separate graphs. The first, is it gonna be 3? Yes. So yeah, 3 graphs. The one of the graphs you've already seen before. That was strong acids and strong base, and that's what this graph looks like here. Now this graph is a bit different to the graph that we have here for strong acids and weak base. And as you assume, it's gonna have start off with a low pH, and then it will have the equivalence point once the H plus concentration is less than the base concentration. But when the pH increases, it's not going to go that high because we have a weak base. So we're starting at a low pH. So in the beginning, there's a very little change in pH with volume of base, and the equivalence point is over a very small pH range because the end solution is not as strongly basic. So we're starting off very low here. The pH doesn't change too much between, what's this now, 25, roughly 25. Yeah, roughly 25 so it looks roughly around 25 centimeters cubed until the reaction goes to completion, right? But the reason why in the beginning there's very little change in pH, and this is pretty much the same for all these types of pH curves, is because in this case the acid is acting as a buffer. And I already explained this in the previous video why it behaves like that. The acid is acting as a buffer until until the A minus base concentration is greater than the H plus concentration. And then the equivalence point, I explained what equivalence point in the previous video. So if you want to check that out. The equivalence point is over a very small pH range because the end solution is not as strongly basic. So compared to this graph, the equivalence point is much greater. Or the equivalence point is the exact point here, but this point where we're going from this value here, I guess, or this range here, when A minus is greater than H plus, is much greater because we're using a strong base here. So the equivalence point is over a much greater point. It's more broad out, right? Whereas in this example here that we're using, the base that we're using, we have a strong acid, so it starts off small from a low pH, but the base that we're ending at a very low pH for a base, roughly pH 9, and that's because we're using a weak base. I think that's pretty self-explanatory, right? So the end solution stops at a pH of roughly 9, and a suitable indicator will be methyl orange as it changes color at a pH greater than the equivalence point. So it makes sense, right? We're going to use a pH of roughly, we want to use an indicator that falls within the range of our equivalence point, And we're not going to use phenolphthalein because that doesn't make any sense, because phenolphthalein is used for a high pH of roughly 8 and 10. So that's going to be there. It doesn't make any sense. So the one we're going to use is methyl orange, because it has an equivalent. It changes color within that pH range. So methyl orange would be the best indicator to use here. So if they ever want you to know about how to describe this graph, we are starting at low pH. Starting at low pH and still ending at a roughly quite a neutral pH. At a quite neutral pH. Right, so next one is a weak acid and strong base pH curve. So as you can see from the graph here, it's very, very similar to the previous graph here. But as you can see, they are very, very similar in some of the traits they have, but also a bit different. The main difference really overall is just the fact that the graph is just shifted up by the y-axis. That's really it. Because look at some things that's going to look is in the beginning there's very little change in pH with volume of base, which is, as I said, is pretty much the same for most of these acid-base titrations, but the equivalence point is over a much smaller pH range because the start solution is not, in this case, it's not strongly acidic. The other one is not strongly basic, it's not strongly acidic, but the key point here, right, in terms of similarity, is that the equivalence point is over a much smaller pH. That's the same as the other value, right? But the only difference here is that it's not strongly acidic. So just the other way around, where this one here we were using a weak base, here we're using a weak acid. So the start solution is approximately pH 3, which is quite high for a acid. So a suitable indicator would be phenolphthalein, as it changes color over an equivalence point. So we would use in this case we would use phenolphthalein, and methyl orange wouldn't be good as an indicator, because methyl orange would be roughly, methyl orange would be, why does it keep going upwards? And that's not very useful to us. Phenolphthalein on the other hand, roughly what? Somewhere roughly around here. And that changes point over our that would change color over our equivalence point. So this would be a good indicator for us to use. So if they ever asked to describe this graph, the key things that you want to say about this graph, if they ever ask describe this graph, starts off as weakly acidic, initial solution, sorry, my handwriting may not be the best. Initial solution has a pH of approximately 3. Here we have our equivalence point. And then we have the last point is that at this point here, we say that our base is in excess. When we've reached the end of our equivalence point here, we say the base is in excess because there's more base than acid, and we have in our burette, right, we have more base than we actually need to titrate this reaction, meaning that it's in excess. The one that's actually at what we call our limiting factor would be the one that gets used up completely, is our acid, the acid in our conical flask that has a certain volume and a certain concentration the concentration we're trying to find out, but it's of certain volume that we're trying to titrate against to find a certain volume And in this case, the title volume people again roughly 25 centimeters cubed. That this is just all roughly the same reaction, right? I just done these graphs and they're not specific values, but the key point here is that the base is the one that's in excess, and here we in this particular case we're using a strong base. So my handwriting is absolutely atrocious. Strongly basic. The final solution has a pH of roughly 13. Alright, hopefully you get on to the base being in excess. The base in the burette is the one in excess, and that's the equivalence point there. Yeah, the base is the one in excess. That's the one that's gonna get, we can have a constant amount of, but the one that's gonna get used up is the acid, because we have less of that. Right. The final example I'm gonna have here is weak acid and weak base. Now, this is the one that kind of falls outside the trends that we usually have. It's very weird graph, and I've done it a little bit of justice here. The graph is actually a bit more distort in this case here. It's actually, it wouldn't be as close as this. It's actually more like this, like how long this equivalence point is. More like and then it reaches a point. But I've done my thing there. I tried. Right, so these titrations start being fairly neutral and end being only slightly alkaline, and it's hard to see the equivalence point as the change is too small. And because the equivalence point, as I say, is we're starting off with a very high pH for an acid and a very low pH for a base. So we're going from roughly 3 to what, 9, and that's not a great change. That's not really a great change at all, really. And these titrations are they're fairly neutral in general, and because the equivalence point is so small, there's not really an indicator that's sensitive enough to pick up on the equivalence point. Instead of an indicator, you usually use a pH probe or pH meter to find the equivalence point here. That's what I'd suggest. So that's really the main. There's nothing really special that I can say. It starts. I wouldn't. The only way I could really say is that it starts at a higher pH than we usually expect, and ends at a lower pH than we usually expect, because we're using a weak acid which has a higher pH than 1, but obviously it's still going to be lower than 7, and then we're going to have a weak base that's higher than 7 but not that much greatly than 7. So it's roughly stays pretty much neutral throughout the entirety of this practical here. Now these titration now it's I wanted to pick up on this here. So there's different types of indicators. The main type of indicators that I usually suggest or to mention in your exam are to do with methyl orange and phenolphthalein. They're the only two that you really need to know off by heart for your exam. Methyl orange being roughly between 2.9 and 4, and phenolphthalein being between 8.2 and 10. But obviously there are many indicators, many indicators. I've only named 2 extra ones really, but in your exam you maybe they may give you a table of different indicators, so it'll give you all the information in regards to, they'll tell you what the indicator's name is and what pH it falls in. It's just understanding, they'll give you the information, it's just understanding that for that pH, like you may get a question. I've seen a couple of questions where they'll show you a graph and they'll ask you which indicator will be the most useful, and you can see from the graph where the equivalence point is. It's just about knowing that we only use an indicator for that where the change in color will occur at that equivalence point. If it can't occur at that equivalence point, we wouldn't use it. So for example, for a strong acid, the top left is of a strong acid and strong base reaction, and in this case we can pretty much use all of the indicators because they all fall within the equivalence point, right? But if we go down to the next one, which is a strong acid, weak base. We can't use phenolphthalein because it doesn't fall within the equivalence point. We can't use alizarin yellow because it doesn't fall within that it doesn't fall within that equivalence point, so it won't show the color change, so it's pretty much useless as an indicator. But we can use bromophenol blue and we can use methyl orange because it does fall within that it does change color within that equivalence point, so those would be useful indicators to show the color change. Remember, the color change is just showing us the end of the reaction where A minus is greater than the H plus concentration, or at that particular point H plus concentration is completely used up, and A minus and the base concentration is greater. A minus is just base, just what we use to represent base. And it's the same principle here. We've got the bottom left is weak acid, strong base, and the only one you can't use there is methyl orange. But I think the principle here is very easy to understand. And the last one, of course, is weak acid, weak base, and of course no indicator. There are very. I mean, technically there probably is one, but really we don't use one. It's not There's barely any indicators that are sensitive enough to pick up these types of. It depends on how weak your acid is and how weak your base is, because that's, using qualitative ways to represent your acid and base are very subjective. How weak is your base, how weak is your acid, and technically there are ones that could potentially be strong enough, sensitive enough to detect the color, to detect the change in the reaction and hence give a color change. But really and truly, genuinely, we just use a pH probe or a pH meter, whatever we want to call it, because that's the best way to tell the color change for this type of reaction. And now that's really it. The only last thing I really want to talk about is the fact that everything I've said in this video, I've already explained in the previous video, but this particular video I was talking about acid-base reactions where we have an acid in our conical flask and we're titrating the acid against the base. But if we drip the acid from the burette, so if we drip the acid from the burette, we just flip the graph. So we'd start with a high pH and finish with a low pH. So that's really, there's nothing really special about it. So if everything that I said applies, it's just the graph would be flipped if we had the base in our remember what you're measuring. This is getting measured from a you always have a pH probe in your conical flask or beaker, whatever. It's usually a conical flask that's used to measure the pH, right? And it's just measuring the pH in the conical flask. And if you're adding acid, in this case, if you're adding acid to it, it will become lower and lower in pH. And the ones here we're starting off with an acid in our conical flask and we're adding more base. So the pH, we're just reading it from the pH probe, and the pH will show us an increase over time. Eventually, it will show a massive increase once we've reached a tighter volume. And it's the same principle here. It wouldn't change the concept of your practical at all. We're just using the different reagents within different glassware. So instead of unloading base, we're unloading acid into a conical flask, and our pH probe will pick it up. So no change to the type of indicators that no, it wouldn't change the type of indicator you'd use, because it's different types of ideally you're still doing the same type of reaction, same type of reagents, just putting them in different ways, and that's it. So that's it. Yeah, hopefully it's